This lesson is on thermodynamics, and you'll see there listed some of the topics that we'll cover. So first we'll begin by distinguishing between heat and temperature. We'll talk about enthalpy and work, endothermic versus exothermic reactions, and then average bond enthalpy. So there's a lot to cover here in this section. We'll go ahead and get started. First is just kind of an introduction to this term thermodynamics, and the definition, very simply, is just the relationship between chemical reactions and heat. So how is heat involved in a chemical reaction? Is it taken in or given off overall? And then ultimately we need to be able to explain why. Why does the reaction need heat, or why does the reaction release heat? Where is that heat even coming from? And so that'll cause us to dive into the world of energy a little bit more. Another question that we'll answer toward the end of this chapter is what causes a chemical reaction to occur in the first place? Why do some chemical reactions just not happen while others do? What is the driving force behind a chemical reaction? To answer that question, we'll need to consider three things. We'll need to consider enthalpy, entropy, and free energy. And those last two are going to come in the very last section of this chapter. But for now, we'll focus on enthalpy, which is related to heat. Okay, first off, the distinction between heat and temperature. So heat is a form of energy, and it is measured in joules, while temperature is a measure of the average energy of the atoms or molecules in a system. So for heat is talking about the total energy of the system, while temperature is talking about the average of a set of molecules or atoms. The Kelvin temperature scale is what we'll focus on, and we can use Celsius as well, but when we talk about the Kelvin temperature, it is proportional to the energy. So if the Kelvin temperature doubles, so does the kinetic energy. Those are directly related. This is not true for Celsius because there are negative temperatures in Celsius, so it's not what we call an absolute scale. We can still say that when the temperature goes up, so does the kinetic energy. But if we want to make this direct comparison, when the temperature doubles or triples, so does the kinetic energy. We can only do that using Kelvin because there's no negative numbers in Kelvin. It is what we would call an absolute scale. So again, the comparison here is that the heat is a form of energy, and we're talking about the total of the system, while the temperature is more of an average for those particles. So if you think about having a little cup of coffee compared to a big coffee pot, they might both have the same temperature, but the big coffee pot is going to have more heat, because it's the total energy of the system, and that's measured in joules. So hopefully that starts to give you some idea of the distinction between heat and temperature. And we'll talk about this more when we talk about something called calorimetry, because in that we use the temperature to figure out the heat by using the mass of the system as well in our calculations. This is what is called a Boltzmann distribution plot. And what this shows us is the kinetic energy of a set of molecules or particles. They could be atoms. They could be electrons for all I know. They're just some particles. And so what you see here are three different conditions, but you have the same set of particles. So on a Boltzmann distribution plot, you're going to have the same set of particles, and you're just going to change their conditions. So in this case, what we're changing is the temperature. So you'll see over here, the temperature is 250 for the set of particles. And then here we have a temperature of 500, and then we have a temperature of 1000. What you're seeing on the y-axis is the number of particles, and then on the x is their energy. So if you look in this first one, what we can see is that the most particles have this much energy, okay, if we take it down to the x-axis. And then you have this many particles with this much energy, and then like this many particles over here with this much energy, and so on and so forth. What we talk about in a distribution plot is this area under the curve. So if we color under this whole curve, this is where all the particles are for this set of conditions. So you can see the most particles are at that peak, which represents this much kinetic energy. If we bring it back down to the x-axis. Okay, I'll keep kind of coloring in here. So these are all the particles. And as we color, you can see that some particles don't have very much energy at all. So if we go down here to the very left, there's some particles that don't really have any energy. And then there's some particles, not very many though, that have like a lot of energy compared to the rest. So if we go over here, to where this red line kind of ends to the right. But most of the energy, or the particle's energy, is right here in the middle. And so where this peak is, if we take that down, I'm going to switch colors now that I've been kind of doodling. If we take that down, that is the average energy. Okay, so the temperature is related to the average energy of the system. Alright, now if we look at a higher temperature, we can see that the hump is lower. And the reason for that is because now some more of the particles got some more energy, so they're spreading out to the right. So if I color that in, let's pick a different color here, you'll see that there are particles way over here with this much energy. Okay, we don't have any specific numbers, but we know it's a lot higher than the energy in the red. There's still some particles under the purple over here, so there's still some that don't have much energy. And then we have lots of particles with this much energy. And this energy at the peak, that's your average, if you bring that down. So you can see that at 500 Kelvin, our average energy is greater than at 250. And we still have some particles that don't really have a lot of energy, but on average, our particles have more energy than they did at 250. We see a big change as we move to 1,000. The hump gets a lot lower, but all the hump represents is the particles at that energy. So now more of our particles are over here with lots of energy. Notice you still got a few straggling particles that don't have a lot of energy. And then you have most of your particles in this energy range. And if you take the peak here and go down, that's going to be your average energy for that system. So what the Boltzmann distribution plot shows us is that at a certain temperature, not all the particles have the same energy. You still have some particles moving slow, you have some particles moving much faster than the rest of them, but overall your average energy is your temperature, and that is related to your kinetic energy. So as the temperature goes up, so does the average kinetic energy. You still got some slow particles, you're always going to have some fast particles, but your average will change as your temperature changes. Sorry, I don't know why this keeps slipping back to the very beginning. Okay, here we are, Boltzmann distribution and temperature. So again, the distribution of the energies changes as the temperature increases, and it actually increases that distribution. So if we go back and look, at 250, there's not much distribution. All your energy is in this tiny range. As your temperature increases, though, you have a greater distribution. So you'll have some particles moving slow and some particles moving much faster. So that distribution is greater. And because the distribution is greater, that's why the hump goes down, because the particles are kind of spreading out in their energies. You have more that are moving fast, still some moving slow, so you have a greater spread, or what we're calling a greater distribution. The average kinetic energy, which you find by looking at that high point, the average kinetic energy of those particles increases as your temperature increases. So be sure that you can read these plots, and these are kind of the key points that you need to know about the plots. Alright, what if two systems come in contact with each other that are at different temperatures? For example, what if you put a piece of ice in your hand, right? You have two systems that are at different temperatures. Those two systems are going to exchange heat. Heat always flows from hot to cold. So the colder system is going to become warmer, and the warmer system will be losing heat to the colder system until they come to what we call an equilibrium, or they get to be the same temperature. So if you look here at the initial conditions, we have a system that's at 350 Kelvin, and we put it up against a system at 450 Kelvin. These arrows are important to note here. So the arrows are showing us how fast the molecules are moving, or attempting to. So you see on the 450 side that there's some longer arrows because these particles are moving faster compared to the 350 where we got the shorter arrows. What happens is these faster moving particles are going to come in contact with the slower moving particles from the other system and cause them to speed up. But when they make them speed up, they have to slow down, of course, because we can't just create speed. So think about if you're playing pool and you have a pool ball moving really, really fast and it hits a pool ball that's stationary, it's going to make that stationary ball speed up, but it itself will slow down or maybe even stop. And that's how heat exchange works. Fast particles run into slow particles and make them move faster, while they themselves may end up being a little slower, until the system gets to where the particles are all moving at the same average speed. Now, of course, you're still going to have some slow particles and you're still going to have some fast particles, but you'll get to the point where the average speed of all of the particles on both the initial conditions is now the same. And so that would be your final or your equilibrium system. So if you look over here to the right, we now have system 1 and system 2 at the same temperature. So that would be your equilibrium state. Make sure you understand how that occurs. It's not this some magic thing called heat is moving. Heat is in the motion of the particles. So the faster moving particles are slowing down while the slower moving particles are speeding up, and that is how heat exchange works. All right, an important law to keep in mind as we move through this entire chapter, and that is the law of conservation of energy. Energy cannot be created, nor can it be destroyed. It can only be transformed from one form to another, or transferred from one system to another. So, when does the energy change? The energy may change during a chemical reaction. When a chemical reaction occurs, we're going to be taking potential energy in the bonds and changing it to heat energy, or we may be taking heat energy and changing it into potential energy. In a phase change, where we're going from a solid to a liquid or a liquid to a gas, we've got some forces holding those particles together, and that has potential energy in it, and we've got to break that in order to melt, for example. And so that would cause a change in temperature, but overall not a change in energy. We're just changing the form of the energy. Also, if you just simply change the temperature of a system, that will change the energy, but that change has to come from somewhere, of course. So you could be putting a pot on the stove. In that case, you're taking the energy from the stove and adding it to the pot. So you would be changing the energy of the system, but overall, no energy can be created or destroyed. So energy, if it changes in the system, it has to come from somewhere, and we call that the surroundings. And it can come in via heat, or it could come in via what we call work. So in any instance where we have something going on, you have the system, and that's the actual reaction that's taking place, or what you're really focusing in on. Sometimes it's a phase change and not necessarily a reaction. And then you have your surroundings, and that's everything else in the entire universe. Now we'll try to simplify and make our surroundings as small as possible, so we'll think about just the area right outside it. If we try to think about the universe, that's a little bit overwhelming, and a chemical reaction that we're doing in the lab is not really affecting the entire universe. It's just affecting its little surroundings. So we'll try to focus in as much as we can. But overall, the system and the entire surroundings is what we'll consider when we say that energy is not created or destroyed. So energy could come from the surroundings into the system, or from the system into the surroundings. but overall it's not going to be created, nor is it going to be destroyed. If we look at a system's energy, we have to consider two factors, and we'll look at those in this equation. So we have the energy in the system represented by E here, and the delta sign stands for change. So if we look at the change in the energy of a system, there's two types of energy to consider. There's the potential energy and there's the kinetic energy. If those change, we'll have a change in our E. And to consider E, we have to think about two factors, heat and work. Heat is obviously, as we spoke before, related to temperature. So the heat change is going to occur when the temperature changes or when the phase changes. If heat is coming in from the outside, it will be a positive value for Q. Or if the system is giving heat off to the surroundings, we'll have a negative value for Q. The second thing to consider when we think about the energy of a system is the work. You can have work done on the system by the surroundings, or the system could be doing work to the surroundings. So if the surroundings do work on the system, then it will be positive for W, and if the system is doing the work, it will be negative. So notice your signs here. If something is coming in, that could be work or heat, then the sign is positive. And if something is going out, that could be work or heat, then that will be negative. Now when we talk about work, how do we measure work done by a chemical system? Okay, so this is key. We have it in a different color down here, if you can see. But work on a chemical system results from the change in volume of a gas. So a lot of times we'll work with gases at a constant volume, and so we won't even consider this W. Or we may have a system where we're not working with gases at all. So again, W would not be considered. However, if we have gases in the system and they expand or contract, we'll need to consider this work value. And we'll look at how to calculate it. But it's going to be positive if work is coming into the system. And if work is coming into the system, that is going to make the volume of the gas go down. Think about a bicycle pump. If you do work on that bicycle pump and push it down, you're making the volume of the gas go down. So that would be work coming in from the surroundings. If the system does work, then the volume will go up and the value will be negative. This would be the case when a gas expands, so it's pushing on the surroundings, doing work on the surroundings, and then your work sign would be negative because the work is going out to the surroundings, not coming in from it. Okay, so take a minute and pause if you need to really understand these signs. It's kind of key to our understanding of energy, work, and heat. Right. If we talk about an isolated system, then energy is conserved. So again, back to our law of conservation of energy. It cannot be created or destroyed. So in a chemical system, which would be like a chemical reaction that we're looking at here, we can have kinetic energy and potential energy. If one of them goes down, the other one has to go up. Or if one of them goes up, the other has to go down. For example, in this decomposition reaction, the reactants don't have a lot of potential energy. However, the products do. And that is due to their bonds. So when we talk about the potential energy in a chemical system, we're always talking about bonds. Okay, so make yourself a note there. The potential energy in a chemical system is contained in the bonds. If the bonds are strong, the potential energy will be low. So remember those plots that we looked at where it dipped as the bond formed? If the bond is strong, that dip will be really low, right? So the potential energy would be low. For example, in the reactants here, there's some strong bonds, so we have a low potential energy. The kinetic energy then can be high, and that's going to refer to your temperature or the particle motion. However, the products of this reaction have a higher potential energy. So that means the bonds are weaker. If our potential energy goes up, then our kinetic energy has to go down. So that means our temperature would decrease. All right, so stated more specifically here at the bottom, as the bonds in the products have more potential energy, they must have less kinetic energy because energy has to be conserved. So if one form of energy goes up, the other one will go down. So that is why the products here would be at a lower temperature. And this is called an endothermic reaction. Because in order for this potential energy to go up, heat has to come in, and that will make your kinetic energy go down. Notice your sign here, your delta H, this is how we measure the energy coming in and out of a system, is positive. And we'll be more specific about delta H later, but I want to focus on the sign here. The sign is positive because the energy has to come in for that potential energy to go up. Where did that energy come from? It came from the kinetic energy or the temperature. So the temperature is going to go down. I really apologize for this flipping back to the front each time. Alright, so in that example that we just saw, we said the heat had to come in to make that potential energy go up. So the products are at a lower temperature than the surroundings now. Right? Because you've got a lower kinetic energy. So what's going to happen is the surroundings, which are now at a higher temperature, are going to give the system some of their heat. And that heat is going to flow until thermal equilibrium is established. So the heat is coming from the surroundings in, so that means the surroundings are going to cool off a bit. Okay, so one more time, if we look at this example, the potential energy goes up, so that means the kinetic energy or the temperature has to go down. So now your system is at a lower temperature than your surroundings, so the surroundings are going to give the system some of their heat, and that's going to make your surroundings cool off. What we feel when we do an experiment in a beaker, when we're feeling the outside of the beaker, we're going to feel the beaker getting colder because the beaker is giving some of its heat to the system. Our hand would also get colder if we left it there. It would take some of the heat from our hand and give it to the system because, again, looking back, the system's kinetic energy went down because it had to have some more potential energy. Alright, what about in an example like this where your reactants have a really high potential energy? That means their bonds aren't as strong. So if you look at the reactants here, their potential energy is pretty high. But when we go to products, we've got really strong bonds. That carbon dioxide, that's 2 double bonds there. Water and oxygen, oxygen and hydrogen in water, those can get really close together, and that's a strong bond. So your potential energy goes down. If your potential energy goes down, then your kinetic energy has to go up because of the law of conservation of energy. So the bonds in the products have less potential energy, so that means the molecules have to have more kinetic. So here our products are at a higher temperature. Right? What are they going to do with that excess temperature that they have? Higher temperature than the surroundings, they'll give off some of that heat to the surroundings. So if we were doing an experiment like this and we felt the outside of the beaker, our hands should get warm because our hand and the beaker are the surroundings and the system is giving off the heat to us if we're standing there. Right? So these are called exothermic reactions. They are giving off heat. Where's the heat coming from? It's coming from the extra energy because the potential energy went down. So the kinetic energy must have gone up. And remember, the potential energy is in the bonds. All right, let's look at an example of a system that would be doing work. So remember, work is done when a gas expands or contracts. So in this example, we have a gas in this container, and then you have your exterior or surrounding gases. The surrounding gases are hitting the container, and the interior gases are hitting the container as well. And those are both causing pressure. If the outside particles are hitting the container more often than the inside particles, that would mean their pressure would be more. So if the pressure outside is greater than the pressure inside, then the piston top would go down. So energy is coming from the outside to the inside. So what would your sign be here? Well, your sign would be positive, right? Because these exterior particles are doing work on your interior particles, causing them to contract. All right? The opposite is also true. If your interior particles colliding with this piston cause greater pressure than your exterior particles, which are also colliding with this piston, then the inside gas is doing the work, causing the gas to expand. So here, your sign for work would be negative, because work is going out of the system as it expands. In the previous example, your work would have been positive, remember, because the system was having work done on it, causing it to get smaller. But here, the system is doing the work, causing it to get larger. So that would be negative. How do we calculate this work, right? From physics, work is force times distance. Okay, so this is just a physics equation. You don't have to know this. We just want to see where this came from. We know that pressure is force divided by area. Okay, that's another equation. So what they did is they took and they replaced this F with pressure times area. And then area times distance is volume, right? Volume is length times width times height, while area is length times width. So if we add another dimension, that's how we get volume. This is the equation that we need to know. Work is the pressure on the system multiplied by the change in volume. And we put a negative sign on here because if the volume goes up, that means the system's doing work, right? So that would be negative work because the work is going out. And if the volume goes down, then these negatives would cancel, volume going down in a negative, and the work would be positive, which is the correct sign if the volume decreased. Right? So that's just showing that negative there we need to make sure we get our sign correct for W. Again, these three are just how they got to this last one, and this is the chemistry equation that we need to know. Work is the negative pressure multiplied by the change in volume. All right, we'll pick back up next time doing some calculations for work and for energy.